Alright, this is the third video in the review for the midterm. This covers Unit 3, which is Atomic Theory and Periodicity. To start with, all of what we know about the structure of the atom and a lot of the other parts of our basic chemistry come from the study of our light. And light really has two natures. It has a wave-like nature and a particle-like nature, which we'll get to in a second. But because light is a wave, it has some of the properties of a wave, such as the wavelength, which is basically the equivalent, the distance between equivalent points, the frequency, which is how many waves pass through a certain point per second, and the amplitude, which is the height of the wave from an origin to a crest or from the origin to a trough. And in chemistry, wavelength is symbolized by lambda, which is like an upside down y. Frequency is symbolized by nu, which looks like a V. And wavelength and frequency are actually related to one another through this relationship that involves the speed of light. C, which is the speed of light, equals the wavelength times the frequency. So if the frequency goes up, the wavelength goes down. They're oppositely related. And the speed of light is always 3.0 times 10 to the negative, or 10 to the 8th meters per second. Both the equation and the what C is will be given on the midterm. So let's use an example to show how we can use this math. A helium neon laser emits light with a wavelength of 633 nanometers. What is the frequency of this light? So, we use this equation. We're given this wavelength, which is lambda, and we know what C is. So we take our equation, C equals lambda V. We plug in C. We plug in our wavelength. Now, the wavelength is in meters. The speed of light is in meters, so we have to put our wavelength in meters, and the easiest way to do that is that we take 633, we multiply it by 10 to the negative 9th, because 1 nanometer, or 1 meter, equals 10 to the negative, let me say that again, 1 nanometer equals 10 to the negative 9th meters. So, write that down. 1 nanometer equals 10 to the negative 9th meters. So if we take our nanometers, we stick on 10 to the negative 9th, we now are in meters. Alright, so we are looking for x, which is our frequency. So to solve for x, we divide both sides by 633 times 10 to the negative 9th. And when we do that division, we end up with 4.74 times 10 to the 14th hertz, or inverse seconds, so seconds to the negative 1. So this is actually a very basic math question. You're given 2 out of 3 variables and asked to solve for the third. Because light is waves, it has a specific type of radiation or type of energy that goes with it that is known as the electromagnetic radiation. And the electromagnetic spectrum describes all the different types of electromagnetic radiation based on their differences in frequency and wavelengths. So this is everything from gamma rays to visible light to X-rays and the whole gamut. Now for the particle nature of light, there were certain properties when scientists were observing light that could not be explained by the fact that it was a wave. One thing was that when you heated an object, you saw that only at certain frequencies of light, that only certain frequencies of light were emitted at a certain temperature. And this ties in with the photoelectric effect, which basically says that electrons will only be emitted from a metal surface when a light of a certain frequency or higher will shine on it. That basically what will happen is, if you have a surface and you have light shining down on it, the electrons will not be emitted unless it is of a certain energy. Once that's the case, then they will leave the metal surface. And Max Planck actually studied this and proposed a relationship between the energy and frequency, which was related through his constant. So, what it said was that energy is equal to Planck's constant times the frequency. And his constant was actually, this should actually read, hold on, let me fix this real quick. His constant was 6.626 times 10 to the negative 34th joules times seconds. Okay? This is actually a superscript, which was a mistake. And what he proposed, or what he said, was that energy can only be absorbed or emitted at whole number multiples of h times v. So 1 times it, 2 times it, etc. And this energy that's required is known as a quantum. Or either that energy that's gained or lost is known as a quantum. Now, let's use this equation to actually solve a math problem. So, calculate the energy of a gamma ray photon whose frequency is 5.02 times 10 to the 20th hertz. So this is very, very straightforward. We know what Planck's constant is, which is 6.626 times 10 to the 23rd, negative 34th, excuse me, times 5.02 times 10 to the negative 20th. We multiply these together, the hertz and the seconds cancel, and we end up with 3.32 times 10 to the negative 13th joules. And joules is a measure of energy. We can also relate both the energy and the wavelength by basically combining these two equations. So our energy is equal to h times c over lambda. All of these equations and the constants will be given on your midterm. Further proof of the particle of nature of light is that when you look at the light given off when an atom is heated, you get to see only certain light that is emitted. And this is known as the atomic emission spectrum. So we have two types of spectrums. We have a continuous spectrum and an emission spectrum. The continuous spectrum here shows all the colors. It is a continuous rainbow. However, the emission spectrum only shows specific energies. And this shows that atoms can only absorb energy in specific quantities, known as quantums. So this is the release of energy at those specific energy levels. And Albert Einstein tied this all together and said that, yes, waves are both particle-like and wave-like at the same time. And that the particles within the light are known as photons. So you can almost imagine these two images if they were overlapped. And the reason why this kind of weird idea came about was because we have observations that give us evidence that it's a wave, and we have observations that give us evidence that it's a that it has particles. So we can't really dispute either or. And so it becomes the fact that it has to be both. Now, all of this talk about light and everything, it did help us become cognizant of what the atom looked like. And there were several different models that were proposed throughout history that really got us to what we know today. The first was Democritus, because we just talked about him in the previous video, and what he said was that an atom was a small, hard particle that was made of the same material, but that was different shapes and sizes. So you could almost consider it as if it was like almost like a pool ball, like to play billiards with. It's a, basically a very, imagine this was shaded in, a very hard, round sphere. And Dalton's built on this. Dalton said that they were indivisible and indestructible particles, and that atoms of one element were all the same, but they were different than the atoms of a different element. So that all of, let's say we have carbon and oxygen, all the carbon atoms are the same, all the oxygen atoms are the same, but the carbon would be different from the oxygen. The next model that came along was J.J. Thomson, and we've already talked about this briefly, the plum pudding model. So you basically have a positive, like matrix almost, a positively charged substance with negatively charged electrons scattered throughout. So again, think of a chocolate chip. Your dough is your positively charged material. The chips themselves are negatively charged electrons. And then we got to Rutherford, who basically disproved Thomson's model, the plum pudding model, and he said that you have a highly packed, positively charged nucleus with the electrons scattered along the edges of the atom. And then that kind of brings us to our more modern debate. The one idea that was proposed and that you've probably learned about before was known as Bohr's model. And what he said here is that electrons, if you have your nucleus, electrons are going to orbit the nucleus in specific rings. It's also called the solar system model for a reason. And that these different rings were going to have certain energy levels. And he called it a quantum number that was assigned to these different energy levels. Well, the problem is that this was great and dandy, but it only worked with hydrogen. Okay? Once you got anything above hydrogen, it became, it wouldn't work. Now, what we hold as our current view is what we know as the quantum mechanical model. This was proposed by Erwin Schrödinger. And what it says is instead of being defined rings, it's more of a probability where an electron is going to be located. And that general area we call an orbital. So instead of thinking of it as defined rings, we now think of it as like a cloud with our nucleus in the middle. And the electrons could be anywhere within the cloud. So here's your positively charged nucleus, and there's a certain, like these gray areas, let's say the shaded areas here would be like your different orbital. That's a probability of where the electron's going to be. And we use 4 numbers to describe the location of each electron in an atom. And you can think of these as coordinates, like almost like a GPS coordinate or an address. Before we get to what those quantum numbers are exactly, let's talk about kind of what we view of the electrons. So if we go with our view and kind of combine it, so we have our positively charged nucleus, okay, and we think about the different energy levels. The ground state is going to be the lowest energy level where the electron's going to exist. At some point, it's going to get energy, that's energy in the form of light, and it's going to jump up to a higher energy level. At that point, it's known as being in the excited state. Now, it will stay in the excited state until eventually the energy will wear off. Goes off in another, often it's seen in the form of visible light, if it is within that range. And then it will fall back down to the ground state. And also, we can't know exactly where the electron is based on something known as the Heisenberg uncertainty principle. This is because we can't measure the position of an electron without changing its velocity. Because the way we measure the position of an electron is by shooting light at it. Well, light will give an electron energy. We give it more energy, it's going to move. So we either know the velocity or the position of an electron, but we can't know both. That's what it's saying. So how do we describe where how the electrons are located? We have 4 numbers that we use to describe. They do have numerical values, but for purposes of this class, all you need to know is what these numbers describe. The first is known as the principal quantum number. This describes the energy level of the orbital. So this is the part that Bohr got correct. The second is the angular momentum, the angular momentum number. This is symbolized by L. The quantum mechanical number is symbolized by N. The angular momentum number describes the shape of the orbital. And we have 4 shapes. We have S, which is a sphere, P, which is almost like a dumbbell, and then D and F, which have more complex shapes. The third number is the magnetic number, which describes the orientation of the orbital. So it's basically kind of telling you where how many sublevels you're going to have. S will have 1 sublevel, P will have 3, D will have 5, and F will have 7. And each sublevel can hold up to 2 electrons. So S can only hold 2 electrons, P can hold 6, D can hold 10, and F can hold 14. And then our final and our 4th quantum number is the spin number. And this describes the spin of the electron. This is the final one that will distinguish between the 2 electrons that are in each suborbital. And why do we care about all of this? Because we can actually figure out where the electrons are based on something known as the electron configuration. It's the arrangement of the electrons within an atom. And the way that these electrons are arranged are based on 3 rules or principles. The first, the main one, is the off-ball principle. And it says that each electron will occupy the lowest energy orbital available. And the orbitals have different energy levels. The next is the Pauli exclusion principle, and states that only 2 electrons can have the same orbital, but they have to have opposite spins. Basically, this is going back to the quantum numbers. It basically means that for the numerical values, that no 2 electrons can have the same 4 numerical values for the quantum numbers. So that means that if you have a suborbital, one will be spinning up, one will be spinning down. And then the third rule is that Hund's rule, and says that each electron must have the same spin before the opposite spin will come into the orbital. So for the p orbital, you have 3 energy levels. If we have 4 electrons, that means the first 3 either have to all be up or all be down before that 4th electron will pair up with one of the original electrons. So they all have to go in the same direction, is what Hund's rule is saying. Now, in order to learn how to fill these, remember that we start at the bottom and we work our way up. And the diagram on the left shows you how those energy levels are stacked. Some energy levels are lower than others, even if they have the same, the orbitals are kind of stacked. Some will have slightly different energy levels, even if they have the same numerical energy level. Like here in this instance, 4S and 4P are a lot lower than 4D or even 4F. So it depends on where they are. And the way that these orbitals are arranged dictates how they get filled. So the little zigzaggy thing on the right shows you the order in which you fill electrons. So let's talk about how do we actually fill electrons and how do we arrange them. So we have 3 basic ways to depict the electron configuration. And the way that this works is you basically start at the lowest energy level and you go through each energy level or each orbital until you run out of electrons. One way that we can show it is with an orbital diagram, and this is where we have the orbitals shown with underneath the different lines here, and we use arrows to represent electrons. Okay, for this instance, this is magnesium. Magnesium has 12 electrons because it's neutral. So we have 2 in the 1s, 2 in the 2s, We have 6 in the 2p, because p can hold up to 6. And we have the remaining 2 go in 3s. So we go until we run out of electrons. The second way we can represent this is just with a basic electron configuration. We give the energy level, which is written as a big number. We give the orbital shape, which is written as a letter, S, P, D, or F. And then we give how many electrons are in that orbital by writing a superscript. So for magnesium, it would read 1s2, 2s2, 2p6, 3s2. And we have, if we add all of these exponents together, they should add up to 12, which is our total number of electrons. Now, we can actually take this, because at times this can get kind of long-winded, and we can write this in a shortened form known as the noble gas configuration. Basically what you do is you go to the previous noble gas. Now remember, noble gases, if you're looking at the periodic table, are going to be in group 18. They're the furthest to the right. So you look at the previous noble gas on the row above, and you start there. So you put the noble gas in brackets as shown here, and then you just go from there. So in our case, neon is the last noble gas for magnesium, and whatever's left over is 3s2. So it's a much shortened version compared to what's in the electron configuration, and it can be helpful at times. So let's look at bromine. Let's do the regular electron configuration and the noble gas configuration. So bromine, if we look on the periodic table, bromine will have 35 electrons. So we're going to go through our little scheme here. This is the scheme that we're going to use. We're going to go through this until we run out of electrons. So let's go back. So we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Okay, so 2 plus 2 is 4, plus 6 is 10, plus 13, plus another 2 is 12, plus 6 is 20, plus, hold on, let me get this right, 4, 10, 12, 18, excuse me, 20, 30, with the 10 here, 35. So we have used up all of the electrons that we have. Now, if we were to go to the noble gas previous to bromine, that would be argon, I believe. Yes, argon. And we basically take out everything up to there. So everything that I marked out has the same, is basically the electron configuration argon. So we start from the next row, which would be 4s2, 3d10, 4p5. So it's a shortened way than what we wrote. Now, based on where elements are on the periodic table, their ending orbital will be different based on their location. We have these different blocks. So the S blocks are groups 1 and 2. The P block is on the far left, or excuse me, on the far right, and that's groups 13 through 18. The only exception is helium should be included really in group 2. So it ends with 1s2. The transition metals, which are group 3 through 12, is what we call our D block, and they're a little bit shorter than the other two. And then our F block is the lanthanides and actinides, and those are the ones that are pulled out from the periodic table on the bottom. Now, the other thing you'll notice is that if we were to write the period numbers, which are the rows, for the S and the P block, the energy level of each orbital corresponds to the row number. For the D block, it is 1 less, so even though you're in the 4th row, you start with 3D. And the F block, remember, that's actually pulled out. So this is row 6, this is row 7. So this is actually, the F block is actually 2 less than the row number. And the important thing is is that you can actually use the periodic table and count through each box as an electron and figure out the electron configuration that way. Now, stability for an electron or for an atom is actually a good thing, and a lot of atoms will try to become stable by giving up or gaining electrons, which we'll talk about in a second. But based on neutral atoms, they are considered stable when you have a half-filled orbital, which for P would be 3 electrons, D would be 5 electrons, and F would be 7 electrons. Also, if they're completely full, so groups 2, 7, 12, and 18 occur in places where electrons are going to be completely full. Now, like I said, electrons are going to lose or gain electrons to become more stable, and when they do this, they become ions. The best way to figure out what the new electron configuration is to either add or subtract electrons based on their charge. And that means you move on the electron or on the periodic table to the new element that has the same number of electrons. So if you add electrons, you're going to increase the number of electrons. So you move to the right in terms of the elements that you're doing. If you subtract electrons, you're losing electrons, so you move to the left. And whatever new electron or whatever new element you land on is going to be the element that you figure out the electron configuration of. Alright, so if we're going to do an example, let's find the electron configuration of bromine. And in this instance, bromine -1. So we're going to move 1 to the left, or 1 to the right of bromine, which will become 36 electrons, and that will be the same as argon. Not argon, excuse me, krypton. So it's the same as krypton. Alright, so we go through and we keep going. 1s2, 2s2, that's 4. 2p6, 3s2, so now we're up to 12. 2p6, or 3p6, 4s2, okay, we're up to 30 at this point. 3d10, which is 40. No, excuse me, this is 20. Now we're up to 30, and then we put the remainder 6 in the 4p. So, this ends up giving us the electron configuration that we would have for basically krypton. Now, we were talking about the periodic table, and there was a lot of, there were a few people that went into the development of the periodic table. The first was on Antoine Lavoisier. I'm not quite sure how to say his name. And he was the first person really to categorize elements, and he put it into 4 groups: gases, metals, nonmetals, and earths. A little while later, John Newland took those same elements that we knew and said, okay, well, instead of doing it by groups, let's arrange it based on their atomic masses. And he proposed something known as the law of octave, which said that every 8th element had similar properties. Then you had 2 very important guys, one of which you've probably heard of before. You had Lothar Meyer and Dmitri Mendeleev. Mendeleev is basically considered the founder of the periodic table, but the 2 of them around the same time came up with the connection between the atomic mass and elemental properties. Mendeleev actually went one step further, and when he put together his periodic table, actually predicted the existence of yet discovered elements, which when discovered actually fit where he put them. Finally, we had Henry Moseley, who proposed to arrange the elements by atomic number versus atomic mass. And that kind of basically gave us the periodic table that we have today. So what does this periodic table look like? Well, we have groups, which are our columns, and we have periods, which are our rows. And we can divide the different elements into three major groups. Metals, which are good conductors of heat and electricity, generally shiny, and they're ductile and malleable, which means they can be bent and shaped. These are typically found, let me get my writing pen. These are typically found on the left side of the periodic table. Then you have nonmetals, which are basically the opposite. They're generally a gas, or if they are solid, they're dull and brittle, and they're poor conductors of heat and electricity. These guys are typically on the right side of the periodic table. And metalloids are basically in the middle. They have both properties of metals and nonmetals. And on the periodic table, you will often see a long black zigzaggy line, and that is the elements along that are considered the metalloids. Alright, so you actually have breakdowns of different groups. So for the metals, group 1 is known as the alkali metals, and they are extremely reactive. They often like to react with group 17, which we'll get to in a second. Group 2 is alkaline earth metals. Again, they're also very highly reactive. Groups 3 through 12 are known as the transition metals. The lanthanides and actinides, the ones that are pulled out at the bottom of the periodic table, are known as the intertransition metals. And that takes care of all the metals. For the nonmetals, we have two groups. We have group 17, which is our halogens. They are highly reactive. And then you have the noble gases, which is group 18. And they are not very reactive. They're actually the most unreactive elements on the periodic table. Finally, metalloids, like I mentioned before, have properties of both metals and nonmetals. And there are about 8 of them. Boron, silicon, germanium, aspartame, antimony, tellurium, polarium, and I don't remember off the top of my head what 8T is. Based on the location of the elements and the arrangement of the periodic table, there are actual properties. There are 4 properties in general of these elements that we can see change across the periodic table to the point that we can actually make predictions about them. And we typically look at them as they move across a period and down a group. The first property is the atomic radius, and it's basically half the distance between two chemically bonded elements. It's basically the radius of an atom. And generally it decreases across the group and will increase across the period and decrease down a group. What's happening here is you have a nuclear charge, which is all your positive charge in the middle of the atom. As you move across a period, you get more and more positive charge and more electrons on the outside in the electron cloud. Because there's a greater number of positives in the middle and greater number of electrons outside, you get a stronger attraction because there's more of each. As you move across, going from, let's say, sodium to fluorine, and that creates a greater pull from the nucleus. So you're going to pull all of the electrons towards you, decreasing the size of the atom. Now, when you move down a group, you get more electrons and you get more parts to the atom. So especially with the electrons, because you have more things there, you have more. You need more room. Because the electrons are negatively charged, they need more space to spread out. The other thing, too, is something known as shielding. You get the electrons closer to the nucleus, getting almost shielding that positive charge from the ones on the outside of the electron. The outside electrons, so there isn't as much of a pull. For the ionic radius, the trend is basically the same, but there's a slight hiccup. For a positive ion, the radius is going to become smaller. Again, you have less electrons. The positive nucleus can have a greater pull on the electrons that are remaining. The negative ion will be larger because you have more electrons. It's going to make it bigger. If you look at your periodic table, a really crude periodic table. Up until, actually, let me redraw that. Okay, so we've got okay, that's a little bit better. Up until about group 14. So we're going to draw it right there. Okay, for a positive ion, it's going to decrease as you get to group 14. Once you hit group 15, it's going to become larger because you have a negative ion. You're going from a positive to a negative, so it's going to balloon up. And then as you move from 15 to 18, it decreases again. So it has the same general trend as the atomic radii, but it has that little hiccup going from between like group 14 and 15, where you go from a really, really small positive ion to a really large negative ion, and then it starts to get small again. Alright, so, and also again it increases down the group. If we were to look at magnesium and strontium, and figure out which one is smaller. Magnesium is at the top of the periodic table, where strontium is further down. That means that magnesium is going to be smaller because it's closer to the top. It has less electrons, so it will have a smaller atom. Between sodium plus 1 and aluminum plus 3, remember, as I was mentioning, as you go further to the right, the ionic radius will get smaller. So therefore, aluminum has a smaller radius than sodium plus 1. Alright, the other two trends, the first is ionization energy. This is the amount of energy that's required to remove an electron. The more electrons you have, the more electrons you remove, the more energy that's required. And it generally increases as you move across a period because it becomes easier and easier for these electrons. They get more electrons, so it's easier for them to keep the electrons versus giving them up. So it's going to be harder to remove them, and it decreases as you go down the group. Again, that shielding is going to create a weaker pull from the from the positive nucleus and the outside electrons. All right, electronegativity is how likely an element is to hog the electrons when it's in a chemical bond. And the big thing to remember here is that fluorine is going to be the most electronegative element on the periodic table. So it generally increases across a period as you get closer to fluorine, and it decreases down the group as you get away from fluorine. So if we look at sulfur and oxygen, and which of the two would have a small electronegativity? So sulfur is here, oxygen is here. Actually, I have that the opposite way around. Oxygen is here, sulfur is here, and then you have fluorine over in this direction. Well, if it increases as you go across and decreases as you go down, that means in this case sulfur is going to have the least electronegative. Is going to be have the smaller electronegativity. Alright, to sum up, atomic size decreases as you move across, as does an ionic size, except for when you go right here between carbon and nitrogen. It gets really, really small here, and then it gets really big as you jump. So it gets really small here, and then it gets really big and gets smaller again as you move across. Electronegativity and ionization energy both increase as you go across and decrease as you go down. Decrease as you go down. Atomic size and ionic size both increase as you move down. And this concludes the third video.